So here's the deal. Tomorrow we'll, still not sure that I'm going to do 33 tomorrow or just do a little test practicing kind of stuff. Still thinking here. Just test practice, really? So aren't you writing now? I could probably drop the test when you write down. You'd be fine, right? No? No? Okay. All right. Well, maybe we'll review a little tomorrow. But this lesson is one of those, kind of like yesterday, it's actually even easier than yesterday. It'll go pretty well, I think, based on past experience. And we'll have plenty of time for questions on homework. So here we go. How you doing basically in the class? You feeling like still a little iffy, or you're starting to get your feet under yourself, or no? Yes? Okay. As I said, it's still in that transition period where, at least when I was in the shoes, I was still trying to get comfortable and getting used to it all. So just stick with it, and we'll see. So the idea today is what's called indefinite integrals. A bit of vocabulary there, but let's start with the idea that all levels of math have inverses. There's all these verbs or actions: add, subtract, multiply, divide. Anytime you do an inverse, it's often the case you want to anytime you do an operation, you sometimes want to undo the operation. You have to have an inverse. There are some things that don't have inverses, like absolute value. It's something you do, but it doesn't have an inverse of it. But most do. So, as you know, inverse of addition and subtraction, multiplication, division, power, roots. Once you get to higher math, you see exponentials and logarithms as inverses of each other. Today, the inverse of taking a derivative is, you could call it one of two things, vocabulary-wise. Either an antiderivative, pretty obvious name, derivative, okay? But this is also known as an indefinite integral. The symbol for which then is this, which is a Roman S. YS, we'll talk about later. Roman S. That's an integral sign. When you do an antiderivative, you're also said to be integrating. All right? Consider this then a way to look at this. Say Joe was looking at his calculus homework. He didn't have his book open, and he saw that in box whatever, that the derivative of f is 3x squared. What was the original problem? It was probably f of x was x cubed, okay? And you're probably right. That would give me a derivative of 3x squared. The first point then is you can always check an antiderivative by saying, what's the derivative of my answer? And wouldn't you agree that if I took the derivative of x cubed, that would work? It would have a derivative of 3x squared. Sweet. Okay. You just took an antiderivative, therefore. You could say that to get rid of the derivative, I integrate it. But whatever I do to one side, I have to do to the other. On this side, then, the antiderivative of the derivative is just the function. Okay, those undo each other. On this side, when you said, what gives me a derivative of 3x squared equals x cubed, you anti-differentiated or took the integral of that or integrated. Are you following me? Just a lot of vocabulary so far. Are we cool? Okay. Now the problem, though, is could it possibly have been x cubed plus 2 to begin? And that would have had a derivative of 3x squared. Yeah? Could it have been x cubed plus 7? Well, that's the next thing, is the mysterious, what I think of as a reverse funnel, or why you put a plus c. All of these, f of x equals x cubed plus 7, f of x equals x cubed minus 7, f of x equals negative 2 sine of 1 plus x cubed, and f of x just straight up x cubed, they all have in common the same derivative. When you take the derivative of all those, they're all going to give you a derivative of x cubed. Even the sine one, just thrown in there to remind you that Sine of x is a function. Sine of 1 is a constant. You with me? Okay. All right. So the thing is then when you integrate, when you're undoing this funnel, all these functions funnel into the same derivative. But when you're undoing that funnel, you don't really know what was here to begin with, if there was a constant there or not. So when you integrate, you don't know what the constant was, or even if there was one. So you always add at the end of your answer this plus c. It's called the constant of integration. It's plus some constant that was probably there before I took the derivative. I just don't know what it was. You follow? So would you then try to integrate or evaluate these following definite integrals? I remind you, this just means this is the derivative, what was the function to begin with, okay? So if the derivative is 7x to the 6th, what was the origin? What is that the derivative of? Remember, after the derivative, the power reduces, then the original probably had a bigger power. What was it? X to the 7th. But again, don't know about a constant that might have been. This says the derivative is cosine. What was the origin? Sine. The derivative was e. What was the original? E dx. Again, could have been a constant there. And this is the great gotcha. Okay? The derivative was 1 over x. What was the original? Okay, natural log of the absolute value of x plus c. Now, why the absolute value? Because remember, the absolute value allows for negatives. Okay, usually you can't put a negative in, but it allows for negatives. Both natural log of normal x and natural log of absolute value of x have the same derivative. Both have a derivative of 1 over x. When you're going backwards in time, then you have to be as inclusive as possible. You have to say, well, it could have had negatives to begin with, so I'll recover my tush and make sure that those absolute values are there. So don't forget that absolute value when you do that natural log. You follow? Okay. Now, as we said, we can't really know what that constant was there to begin with unless you had a little more information. Now consider graphically. Say you knew the derivative was this, and I asked you, what could the original function be? I could have had, if the derivative was 2x, give me some possibility for what f of x could have been. Okay. F of x could have been x squared. Give me another possibility. X squared plus 1. Okay, could have been x squared plus 1. Give me one more. X squared plus a billion. I like it. F of x equals x squared, not drawn to scale, plus 1 billion. Okay, now then, the only way I'm going to be able to figure that out is if they give me, besides what the derivative was, one other piece of information. They said, okay, yeah, the derivative is 2x, and by the way, an original point, notice it says f, not f prime, an original point is when x is 1, y is 7. Now, the minute they give you 1, 7, it starts to nail down, that's not it, it starts to nail down one possible answer it could be. It could only be at that point 1 anymore, and now you can figure out what that is. So the process would go something like this. You first anti-differentiate. If I want to get rid of the derivative, the question says find f, which means not f prime. What's the opposite of f prime, or the opposite of the derivative? The integral, or the antiderivative. Whatever you do to one side, you do to the other. So that puts me where? F of x equals x squared plus c. If the derivative is 2x, the original must have been x squared, but I don't know that plus c. Now we use the initial condition, shortened to initial condition. Use the initial condition, and that is something like when x is 1, f is 7. So where do I put the 1? Where do I put the 7? The 7 goes in for f, and the x is 1, leaving you with c. So c must have been 6. And therefore the function must have been x squared plus 6 if it has a derivative of 2x and passes through the point 7. You follow? All right, try it on your own. Try to the back. Go to the back and try that. Well, try all three. I think it should go okay. Try those three. Talk them over with each other. Say, hey, what did you get for that one? Or what did you get for this one? Or, hey, how you doing today? And we'll go over them in a bit. Let's see here. The first thing I would do is say, all right, if I want f, I'm going to anti-differentiate both sides. On the left side, the antiderivative of the derivative is the function. What is the antiderivative of 1 over x? Natural log of the absolute value of x. Did you remember your absolute value? Okay, super. And then how do you find how do you use the initial condition? 7 is the natural log of 1 plus c. What did you get for your constant of integration? Plus c is the constant of integration. 7. Why? What happened to the natural log of 1? 0. Why is that 0? Because that's what I was told, and I just go with it. Why is natural log of 1 0? E to the 0 is 1. Right? So when you do natural log, you're saying what power of e makes 1? So 0. Well done. Okay, sorry, I'm not very good at seeing who's talking. All right, so you can see then that e is, or c is 7, yeah? So your function is the natural log of the absolute value of x plus 7. Did you agree with the first one? Cool. Okay, if you anti-differentiate the second one, the antiderivative of the derivative is the function. What's the antiderivative of negative sine x? Cosine gives you a derivative of negative sine, so it must have been cosine plus a constant. If I plug in negative 3 for the function, pi for the x, what is cosine of pi? Cosine of pi, your trig skills are lacking, some of you. Cosine of pi is negative 1. Remember, that's here. Cosine is x. X is negative 1 there. So if negative 3 equals negative 1 plus c, then c is negative 2. Oh, maybe you're jumping straight to the answer. That's what you said too. I see. Okay, so f of x equals cosine of x minus 2. How'd you do that? Okay, anti-differentiate this bad boy. Normally this would be a little beyond the scope, but we've done this derivative so many times I thought you'd probably recognize it. What gives a derivative of 1 over 2 root x? Root x. We've done that derivative so many times that I thought you would probably recognize that. What then, using the initial condition, 7 equals root of 25 plus c. What is your c? 2, and therefore your function is the square root of x shifted up 2. How'd that go? All right. I threw one AP multiple choice kind of question on here to get a flavor for how this can look. Give that some thought. There are a couple ways to go at this problem, so I'll let you think about it, talk it over, and well, if we have 2 strategies to go at this, all the better than just one. While you're thinking about this, if you could eliminate some choices, also think about how you might be able to do that. Ask you how you might do that. Okay. Give me one strategy to solve this problem. Throw it out there. What? X cubed. Okay, so how did you know x cubed? Okay, so you know, so you're actually integrating, so that sounds good. Say I integrated. Over here it's not a prime, it's derivative still though, so you get y equals, what is the antiderivative of 3x squared? X cubed, and what's the antiderivative of 1? X, negative x, plus a c. How do I find the c? Plug in, yeah. Negative 1 equals 1 minus 1 plus c. That implies that c is negative 1. So y is x cubed minus x minus 1, which tells me b. Give me another way besides like doing that. Okay? Instead of integrating, try derivative. What's the derivative of this? 3x squared. 1. Minus 1. Is it in the running still? Yeah, that has the right derivative. What's the derivative of this? 3x squared minus 1. That has the right derivative where it's still in the running. What's the derivative of this? Out. Out. 3x squared and nothing. Out. Okay, so now then how do I decide between A and B? At some point we're going to have to use this. So how do I use that in this frame of mind? This frame of mind. Plug it in and see which one yields a negative 1y. So if I plug in a 1 into x here, I get 1 minus 1 plus 1. What's 1 minus 1 plus 1? 1, and so that yields the wrong y, okay? Whereas 1 minus 1 minus 1 is negative 1, that yields the right y. So you could go at this a couple different ways, but the answer is most definitely B. You follow? Okay. Alrighty. That's that. So let us go to questions on sets. What do we got? What's the oldest? 30?
Yeah.
30. Let's get set 30 questions. Here's one of my calculators. If anybody borrowed one of my calculators and took it, please make sure I get it back. Okay, 30. Questions on set 30. 13? Okay. I need to actually put this in front of me. Yeah, left side. Okay, 30. Yeah, oh yes, you're raising your hand. That's great. Go ahead. 24?
22.
22. Did you say 24? Okay, sorry, I'm just wondering. Did I get that? Okay. 14? Okay. 23? Okay. I'm going to go back and get another copy of this. All righty, here we go. Set 30, number 13. Okay, so what I'm getting at here is two different skills I'd like you to have. Being able to solve a non-function for a function. That's a skill in itself that you're going to need to get better and better at as we get closer to implicit differentiation. 4y squared. So there's this whole field of graphs that you've never even seen before, but they're called closed curves, where it might look something like this big crazy thing, you know. It's a limited closed curve, and it's obviously a non-function. And so in order to work with that, sometimes you need to be able to put it in a function notation and solve for y. I know some of you are saying, well, I don't need to solve for y, I just put it in my calculator. Well, that's great if your calculator does conics, but it doesn't do all closed curves. So my point is you need to be able to do this. Period. Solve this for y. We're going to solve this for y. This is a ellipse, so it doesn't work like that. But we're going to solve for y and then find the slope at 0.5. So first, solve for y. Solving for y means we need to start by getting the y's on one side and everything else on the other. And this is actually not too bad because I don't need to complete the square. That's delightful. Sometimes you have to complete the square. So I could divide by 4. Whether you want to put each one over 4 or all over 4 is up to you. And square root. Now when you square root, it's positive for the top half of the curve. And I'm going to call that negative x squared plus 2x plus 3 all over 2. Or negative x squared plus 2x plus 3 all over 2. You follow? All right, then. In your calculator, then, if you were to plug this in your calculator, I wish I had my calculator up and running. Oops, FERPA. If you get this in your calculator in the graphing screen, you should, I imagine, get an ellipse. And then the next skill is the part that I'm getting at, find the slope. That's why you use your calculator to find a derivative at a point. When you find the slope, you're finding the derivative at a point. You need to be able to do that in your calculator. I'll do one of the curves, and then as long as you follow along and understand, that's all I ask. So make sure you can do this pretty soon. Imagine in a minute. Let me look more time at this thing. Negative x squared plus 2x plus 3 all over 2. There we go. Maybe not. Come on, baby. Help a teacher out here. I think it's there. Come on, Pokey. Okay, yay! All right, so here we go. Menu. Okay. Sorry, I should have had this up. All right, so I'm going to go to the graphing menu and plug in or give myself the function square root of negative x squared. I think then it was plus 2x plus 3. Is that correct? Or is it minus 3? Yeah, plus 3. All of that divided by 2. If I go to graph that, boom. If I then, in the next one, type in the negative version, negative x squared plus 2x plus 3, all divided by 2 outside the root. Hopefully that'll complete the ellipse and look like that. You tracking so far? Now, you can see then that at 0.5, there will actually be, oops, I can't do that, 2 possible slopes. If I move this over here, there are actually 2 possible slopes. This is a non-function. So you're going to go to your home screen and calculate the slope twice. To do that, you go to, in the Inspire anyway, in the 84 you go Math 8. In the Inspire you go Menu, Calculus, Derivative. The variable is x. The value is 0.5. First derivative is good. And when you do that, it's then going to say, all right, what function? So to get the first function, go to vars and call up f1 of x, give it x. And it'll say, hey, the slope there is 0.129. Give me 3 or more decimals. Did you get the same result? Okay, you could then do the same thing at the second function. Oops. 4, 1, tab, 0.5, enter, and use F2. And, oops, darn it, I don't know why I just did that. And it's negative. So how'd that go? That's what I'm looking at. So as far as notation, I would say y prime, maybe I'd call it y1 prime at 0.5 is roughly 0.129, and y2 prime at 0.5 is roughly negative 0.129. Does that make sense? Does that go okay? So be able to solve for y, including completing the square, which we didn't have to do here, but also then use the calculator to find the slope at a point by taking the derivative. Cool? 24. 24 is this. We were just talking in the math meeting about how we're not sure if the geometry skills are as strong as we'd like them to be. What do you think? How do you think your geometry skills are? Okay. So we would hope that if you couldn't remember the quick algorithm, that you could still work your way through this by good problem solving, but then we thought, yeah, I don't think they would have any idea how to work this way through if they didn't remember. The whole idea is based on similar triangles. If you connect this and this, they are similar triangles, and you can use proportions, and that's where the idea comes from. But again, I don't know if that's going to be there for a lot of people. Would you like to use a similar triangle approach, or just what's the rule so I can use it? What's the rule? Okay. So if that's x, PC is x minus 1, and BC is x minus 2. The rule for the algorithm is that the outside times the whole of 1 will equal the outside times the whole of the other. Now, this is what I mean then. For this guy, the outside is the segment outside, which is x minus 1. The whole is the sum of the whole segment, which is x minus 2 minus 1, plus x minus 1, which is 2x minus 3. You see? On the other one, it's not a secant, it's a tangent. It touches in one place. So things are a little different. What's the outside? X. What's the whole? X. Okay, and so you would approach it that way. But again, I don't usually remember that rule. I just draw in some lines, say, all right, the triangles are similar. Draw the triangles off to the side, decide what's proportional, and that's how I'd work my way through it, problem-solving style. 22, question on 22, yes? All right, probably let's start with going the answers here. I gave you a function that looked cubic in nature with zeros at 1, or negative 2, 0, and 3, yay? Reviewing the big ideas of reciprocals. Where the original has x-intercepts, Where the original has x-intercepts, the reciprocal will have asymptotes. So we'll have 3 asymptotes at negative 2, 0, and 3. Next big idea. Where f is negative, 1 over f is negative, and it behaves in an opposite way. Big negatives mean small negatives, and small negatives mean big negatives. So the graph would look like this. In here, positives give positive reciprocals. You'd have small and small here and here, which would mean reciprocals would be big and big. And then the reciprocal of this, whatever it might be, say it was 2, then the reciprocal would be 1/2, yeah? So it's going to go in there. It's not touching the axis. Don't come in all the way to the axis. Same kind of idea here, where this is negatively small and negatively small. The reciprocal will be negatively large and negatively large. Reciprocal of this, maybe it's -2 then. The reciprocal would be -1/2. So it might look like that. And then this positive and opposite behavior. Big goes to small and small goes to big. How'd you do there? Did you get that? You in? Yeah. Okay. Now let's graph the derivative. Let's start with zeros. How many places does this have flat or zero slope or horizontal tangents? 2. There's 1, 2 horizontal tangents. Eyeballing it, so maybe -1-ish. I don't know for sure, but somewhere around there. And 1.5-ish. Cubes don't really have symmetry like that, so I'm taking a stab at it somewhere in there. You with me? Okay. Slopes are positive for x is less than -2, which implies the derivative is positive. Therefore, the graph of the derivative is above the x-axis. So the graph of the derivative is up here. And as far as what kind of numbers, these are really steep. So if I were to put a slope to this, it might be up 8/1. So that would be something like this, until it starts to get flatter and flatter and flatter and approach 0. Then I start to get negative slopes where the function is decreasing, the tangent slopes are negative, the derivative is negative, so the graph of the derivative is below the x-axis. Good job. That is, by the way, what you sound like. Below the x-axis. Then you start to look at positive slopes, positive derivatives, and boom. Tell me in terms of what the graphs look like and powers, why my answer makes sense. Because that looks like x cubed. And so the derivative of x squared, totally logical. Right? It's just a matter of where it's at. Does it make sense? Okay. 24 is, that was 22. Checkity, check. Let's go to 14. 14 is, out of the book, log in root of x plus 1. This is good pre-calci math toolkit problems. Composition and domain and range, this is something we need to have more and more solid. So here we go. F of g, log. Is that g goes into f or f goes into g? G goes into f. If you like, you could collapse an array this way. So g goes into f. That yields the natural log of the square root of x plus 1. Oui. All right, that actually has this. Ooh, this one's tough. Should we do domain and range in this and then go to graph? What do you think? Okay, so domain, this has 2 possible problem areas. There's the root and the log, yeah? For the root purposes, I can't have a negative. So that implies right there that x must be greater than, what about equal to? Equal to -1. Okay, that comes from me mentally saying x plus 1 has to be greater than or equal to 0, which implies x has to be greater than or equal to -1, right? Here's the problem though. For the log, the root, I can't have the log of 0 or negative. So that means square root of x plus 1 cannot be 0 or negative, yeah? So what does that imply? That x must be strictly greater than -1. So the equal to now is out, and my domain then is x is strictly greater than 0. Not 0. What am I dumb? Sorry, I just said x is strictly greater than -1, not equal to equal. You follow? The range, that's the domain. The range, a log graph normally looks like this. Oui. Okay. The question then is, all right, does the square root change that? Does the x plus 1 change that? Or can I still get negatives and positives and all that stuff? What do you think? Can I get negatives out of this bad boy? When do you get these? How is this kind of negative y achieved when you take the log of what kind of numbers? Between 0 and 1. Okay, so my question really amounts to, in order to do I get those negatives, well, that amounts to, can I get anything between 0 and 1 out of that? Can I? You can. Okay, so say example, if I put in negative 3/4. Negative 3/4 plus 1 would be 1/4. Square rooted would be 1/2. And so the log of 1/2, that's one of those negative values. So to answer my question then, can I get negatives? The answer is yeah. Fog will be all reals. I will get negative y's, positive y's, 0 y's, and so boom. That was tough. Golf. Fog and golf. Now we're on golf, which is g of f, or f into g. If I put f into g, then I'm getting this. The square root of the natural log of x plus 1. Now, I have still two issues. For the log, what's the implication? X must be greater than 0. For the root, what's the implication? That the inside the root, which is this whole thing, must be greater than, can it equal 0? It can equal 0. You can square root 0. So that implies then that, let's talk about what x is then. X is, the natural log of x has to be greater than negative 1, which means x has to be, you could do E, you're almost there, not E. E to the negative 1. X has to be greater than or equal to E to the negative 1, or 1 over E. And if it falls below that, let me explain here. Say x was 1 over E squared. That's less than that. Well, if I put in 1 over E squared, or E to the negative 2, what if I had e to the negative 2? What's natural log of e to the negative 2? Natural log of e to the negative 2 is negative 2. Negative 2 plus 1 is negative 1, and I'm in trouble. Square root of negative, right? So that's how this is working here. X has to be greater than or equal to 1 over e, because that's going to make this negative 1 or more and make it all cool. So your domain is the rather difficult. X must be greater than or equal to e to the negative 1 or 1 over e, because that's going to satisfy both conditions, positive in the log, but also positive or 0 in the root. That's a tough one. The graph. What comes out of this? What comes out of a square root? Do you get negatives out of a root? No. Okay. What about 0? Is there a way I'm going to get a 0 out of this? Yeah. If I put what in here? When I get a negative 1, which would be I put in originally in for what x? E to the negative 1. If I put in my e to the negative 1, which is allowed, I get negative 1 plus 1. It is 0. So what's the least y I get? 0. Goff is greater than or equal to 0. And that might have been the hardest problem on this set. That was tough. Okay? You follow? That was tough. I mean, that's not just me saying. I thought that was hard. 14, 23. 23. Is that changed any? No. Okay. Use a graphing calculator to solve the system. If you have an Inspire, you can plug in conic sections in the actions. Where do you go for that? I felt like this was so easy that I didn't need to go to conic mode in my calculator. I just did y1 is the square root of 8 minus x squared. y2 is the negative square root of 8 minus x squared. And y3 is log of x. And when I did that, then you should get intersection points like a circle and two and a log, so something like Control G. Okay, so what did I say? The square root of 8 minus x squared. Control G. Negative square root of 8 minus x squared. Boom. And then Control G. Natural log of x. All right, so how many intersection points do I expect? 2. Okay, so you go to Analyze Graph, which is in the menu. Analyze Graph, intersection points. If you say, sure, graph line, graph curve, and the intersection is here, then you'll get one solution. You should be giving x and y. Then if you do the same thing again, menu, oops, not second menu, just menu, analyze graph, intersection, say I want this graph and this graph, intersection point, boom. That's the process. If you have an 84, it's different. And if you have an 84, then let me know if that's your question. Very cool? Okay. That's pretty good. Let's go to 31 and at least maybe get a 1 or 2 done. Questions on set 31? Did you say 1? Oh, never mind. I must have heard so. Anybody have questions on set 31? Or, oh, geez, I didn't do set 31. I went out on a date with my girlfriend yesterday. Which one is it? There you go. Never mind. Okay. Questions on 31? Yes. Oh, you're raising your hands. That's ridiculous. Go ahead. Just shout them out. 21. Yes. Kenny, hit me. 1. 21 and 1. 10. That's probably as much as we're going to get to, if even that much. But we'll see. 21. Let's see. What's 21 I can score from 21? A rational roots theorem. Holy cow. Do you even remember the rational roots theorem? Probably not, because that's why you're asking. Okay. Now, actually, it says find the real roots. So how many? Every cube, this is called the fundamental theorem of algebra. And it says basically that there's a direct match between the power of a polynomial and how many solutions. A cube must have 3 solutions. Now that said, they don't have to be real solutions. You can have imaginary solutions. So they're asking me to find the real ones. I would normally, if they didn't say use the rational roots theorem, I would factor this by grouping myself. Do you remember how to do that? It looks like this. And that would then tell me that the rational roots are, there's 1. X equals 1 is the only rational root. Root 2 is not rational. Did you see that too? I bet you saw that yourself, huh? Yeah, you did. However, it didn't say use factoring or all the tools at your disposal. It said use the rational roots theorem. So, if you recall, the idea is you're trying to figure out what to synthetically divide by, and the rational roots theorem guides you. This is what you divide by. It says you divide by stuff that amounts to factors of the last number over factors of the first. In this case, then, that would be factors of the last number, which is 2, over factors of the first, which is 1. So the rational roots theorem tells you that if this is going to synthetically divide cleanly, would you just put it on the table, please? Thank you. What's that? Did she ask me to collect it? I'll take it just in case. Thank you. If it has rational roots, there will be one of those 4 numbers. So if you try, for example, 1, Do you remember how are your synthetic division skills? Are they there, or do we need to review that? Okay, they're there? Okay. So if you bring down, multiply, recorded here, add. Multiply, recorded here, add. Multiply, recorded there, add. This tells you actually two things. First of all, x minus 1 is a factor, and it also tells you that when you take it out, what's left is x squared plus 0x plus 2. This tells you the depressed equation as a result of dividing x minus 1 out. From that, you can see that these aren't rational. If you solve this, they'd be irrational. So your only solution, your only rational root is x equal 1. Wait. How about 5 times for 1? I don't want to do a bad job of it. Let's see. I can maybe get you started here. You have a 10 by 10 sheet, and you're cutting squares out so that when you fold along the what's left, you'll start to get a box. This square would be the base. This flap would fold up, fold up, fold up, fold up. So if this was 10, and you took an x out of each side, what's this side of the base? 10 minus x or 2x's? 2x's. This was 10, took away an x. This also is 10 minus 2x. And what's the height? X. I don't know if that gets you going enough, but that's all you have to do then is write the volume as length times width times height. And so that's 10 minus 2x quantity squared times x. And then later on in calculus, we'll optimize that, find the maximum volume with the best x. That's pretty much all we're going to hit. So I didn't get through 31. You can keep 31. 30 is due. Have a great day. Is that what? Yes, the set you got today is due tomorrow. Tomorrow, the homework that you get tomorrow won't be due until Monday. Yeah.